I welcome you in this lecture on directional couplers. So figure 1 shows a directional coupler. As can be seen from the figure that a directional coupler is a 4-port junction. We have port 1, port 2, port 3 and port 4. This is the port number 4. So is a 4-port waveguide junction consisting of a primary waveguide. Ports 1 and 2, for example, they correspond to primary waveguide, and ports 3 and 4 correspond to a secondary waveguide, as can be seen from figure 2. Ports 1 and 2, this is our primary waveguide, and ports 3 and 4, they correspond to a secondary waveguide. Now when all these ports, say for example port 2, 3 and 4, when all these ports, if I terminate it with some impedance ZL, which is same as the characteristic impedance, if ZL is equal to Z0, again if I terminate port 4 with some load impedance which is same as characteristic impedance, and port 3 with some load which is same as characteristic impedance, and if I feed a signal at port 1, what happens is that there are no reflections coming back to port 1. All I mean is that there is a free flow of power between ports 1 and 2. So the signal reaches, as is shown by this arrow, that some part of the power reaches port 2 and some part of this power gets coupled to port number 4. But there is no transmission of power between ports 1 and 3. So ports 1 and 3 are, this is port number 3, as can be seen here. This is port number 3. So all I mean is that if I feed a signal at port 1, assuming that all these ports are terminated at their characteristic impedances, power flows from port 1 to port 2 freely, and also power gets coupled from port 1 to port 4. This is port 4. And there is no power that reaches from port 1 to port 3, or there is no flow of power from port 1 to port 3. So port 3 is called as isolated port, port 4 is called as coupled port, and port 2 is through port. If I feed a signal, I repeat, if I feed a signal here, it reaches to port 2, it also reaches to port 4, and nothing reaches to port 3. So port 1 and 3 are isolated. So likewise, if I feed a signal, say for example for a bidirectional coupler, if I feed a signal at port 2, it reaches the port number 1, and some part of the signal gets coupled to port number 3, and no power reaches port 4. We don't receive any signal in this direction, so port 4 receives no power. So in terms of S parameters, I can write S13 is 0 as they are isolated, or for that matter I can also write S24 is 0. So ports 1 and 3 are isolated and ports 2 and 4 are isolated. Now say for example these ports, port 2, port 4, or for that matter port 3, they are not terminated at their characteristic impedances when I feed a signal at port 1. What happens in that case is, let me erase it first. Let me erase this thing. So say for example I am terminating this port 2 with some impedance ZL which is not equal to characteristic impedance, and when I feed a signal at port 1, this signal, as I said, the power flows to port 2, but since ZL is not equal to ZL, so there will be reflections. We'll be having a reflected wave as well. So this reflected wave can reach to port 1, and some part of this energy can get coupled to port 3 as well. So it is because of reflections we have another wave as shown in this blue color. This wave can reach port 1 and this can again reach to port 3. So in this case, we receive some power at port 3, which ideally is not the case if we terminate port 2 at its characteristic impedance. So in a nutshell, if I feed a signal at port 1, some part of the power reaches to port 2. Let me raise it first. So if I feed a signal at port 1, it the power flows to port 2, and some part of this power gets coupled to port 4. So this coupling usually is achieved by making a hole in the primary waveguide. So we can have two holes, for example, we can have four holes in the main waveguide, this in the primary waveguide. In this primary waveguide, we can have more holes. For example, we can have two holes, four holes, and the number of holes designates its name. For example, we can have a two-hole directional coupler, we can have four-hole directional couplers, depending upon the number of holes in the primary waveguide. We'll discuss two-hole directional couplers after this. So as I said, power, a signal source or a signal fed at port 1 reaches port 2, and some part of it gets coupled to port 4, but we don't receive anything at port 3. Power received at port 3 is 0. Likewise, if I feed a signal at port, if I feed a signal at port 2, we receive some power at port 1, and some part of the power also reaches port 3, but nothing reaches port 4. Power received at port 4 is 0. Now the performance of a directional coupler is usually defined in terms of two parameters. Two parameters. One is the coupling factor, and second is the directivity. Now if I designate these powers, power fed at port 1 as P1, the input power as P1, P2 the power received at port 2, P4 the power received at port 4, and P3 the power received at port 3. Then the coupling factor can be defined as coupling factor. Coupling factor in decibels is 10 log 10 P1 upon P4. P1 is this input power and P4 is the power that's coupled to port 4, this P4. And likewise, directivity, which is the second parameter in decibels, is 10 log 10 P4 upon P3. P4 is the power received at port number 4 and P3 is the power received at port number 3. So this is coupling and this is directivity. But it is to be noted that ports 2, 3 and 4 are to be terminated by their characteristic impedances. So for a typical coupling value of 3 dB, for example, we have a 3 dB coupler. A 3 dB coupler would mean that coupling factor C, as we know, is 10 log 10 P1 upon P4. That would mean 3 is 10 log 10 P1 upon P4, implies log to the base 10 P1 upon P4 is equal to 0.3, which in turn means P1 upon P4 is 10 to the power 0.3, or P1 upon P4 is this means P1 is the power here and P4 is the power received here for a 3 dB coupler. P4 is half of P1. So that means half of the power fed at port 1 is being received at port 4 and half of the power naturally would be received by port 2. As port 3 is an isolated port, that means power received here is 0. So this is what a 3 dB coupler means. Half of the power is being received by port 2 and half of the power is being received by port 4 when power is fed at port number 1. Likewise, for a 20 dB coupler, we can use the same formula. For a 20 dB coupler, that is C is equal to 20 dB. P4 would be P1 upon 100. So 1/100th of the power fed at port 1 is being received at port 4 for a 20 dB coupler. Another parameter sometimes is used which is called as an isolation. This is also used for describing a directional coupler. Directive properties. It is defined as isolation is 10 log 10 P1 upon P3. This is also in decibels. So ideally its value must be infinity. It must be as high as possible. As I said that ports 1 and 3 are isolated, so 10 log 10 P1 upon P3 ideally should be having a high value. So isolation of a directional coupler ideally should be very high. Generally the power fed at port 1 is called as incident power. The power received at port 3 is called as backward power or back power. The power received at port 2 is called as received power, and the power received at port 4 is called as the coupled power. Relationship between isolation, coupling and directivity is as isolation in decibels is coupling in decibels plus directivity in decibels. As we know, coupling is 10 log 10 P1 upon P4. Directivity is 10 log 10 P4 upon P3. So I can write it as 10 is common, 10 log P1 upon P4 plus log P4 upon P3. So 10 log m plus log n is log mn, log P1 upon P4 into P4 upon P3. So P4 cancels, it is 10 log 10 P1 upon P3. This is log 10. So it is 10 log 10 P1 upon P3. Now if we look at the definition of isolation here, isolation is also 10 log 10 P1 upon P3. So we have proved that isolation is coupling plus directivity. So next we'll discuss a two-hole directional coupler. Now let's discuss a two-hole directional coupler. Two-hole directional coupler. Now, as said already, a directional coupler has basically a primary waveguide consisting of ports 1 and 2 and a secondary waveguide 3, 4. This is port 1, port 2, they correspond to primary waveguide, and ports 3 and 4 they correspond to secondary waveguide. So for a two-hole directional coupler, we make two holes, one here, another here, two holes both in the primary and secondary waveguides. So I connect to this thing like this. So now there are two holes, one here and another here. We have two holes for a two-hole directional coupler. Now the spacing between these two holes, between the centers of these two holes, is L has to be an odd multiple of lambda g upon 4. Now if a signal is being fed at port 1, say for example some energy, microwave energy is fed at port 1, some part of this power or energy directly reaches to port 2, and some part of the energy gets coupled through these holes to the secondary waveguide 3-4. So what happens is that when it reaches the secondary wave, there are two possibilities. This energy here can move in forward direction. It can move in the backward direction as well, as there are two paths. It can go in the backward direction as well. Likewise at slot number 1, if let us name it as slot number 1, slot 1, and it is slot 2. So likewise at slot 1, this wave again can get divided in a backward wave and another part as forward wave. Let me use a blue pen, rather a red pen here. Not red, let me use different pen. Let me use a black color here. So all I'm trying to explain is that at these points there are two possibilities. The wave goes either in the right direction, forward direction, or in the backward direction. Here again at this point in slot number 1, the wave can go in the forward direction towards right, or it can go in the backward direction. If I designate these forward waves by, say for example, by F1 and F2, F1 and F2, these forward waves F1 and F2 designated here in black color and other in this color F2, they add up in phase at port number 4. So we receive some power at port number 4. Now what happens at port number 3 is that the backward waves, as let it be B1 and let this be B2, these backward waves, when they reach port 3, they reach port 3 out of phase. So these backward waves cancel. B1, B2, they cancel out and we don't receive anything at port 3. So this is what we said earlier, that if I feed a signal at port 1, we don't receive anything at port 3, but yes, we receive energy at ports 1 and ports 4. Let me redraw it. So I'll draw it again so as to explain this cancellation of the waves. Let me draw it neatly this time. This being our primary waveguide, and this being the secondary waveguide. So we have the first waveguide 1, 2 as the primary waveguide, 3, 4 as the secondary waveguide. Then I said because it is a two-hole directional coupler, we need to have two holes in the primary waveguide and we need to create two holes in the secondary waveguide as well. So let me combine it. Let me join these pointers. So we have this as our waveguide. This is how it looks. So if I have a signal, if I feed a signal at port 1, let me draw it by a black marker. So if this is the signal which is being fed at port 1, it flows to port 2 directly. And some part of the energy, as I said, gets coupled to the secondary waveguide. To the secondary waveguide. 1, 2 is our primary waveguide. So some part of this energy gets coupled or leaks through these holes to the secondary waveguide 3, 4. So at these points, there is a possibility that the wave will again split in forward and backward directions. Let me use a red marker for the backward wave. This is the backward wave, B1. Again, there is a possibility that it can split. Some part of the energy will reach backwards, will move backwards towards port 3. So this is B2. And again, there is a possibility that some part of this energy moves in the forward direction. This is the forward energy. This is F1, this is F2. Now, so far as F1 and F2 are concerned, as I said, F1 and F2, they simply combine here to give us some power at port 4. Now, the fact of the matter is that these two signals, these forward signals F1 and F2, they add up in phase, while as B1 and B2, they are out of phase. When they are out of phase, they cancel each other. They cancel each other so that there is no power received at port 3. These add up, F1 and F2, they add up, and we receive some power at port 4. Now let us see how the phase difference between the two waves B1 and B2 is 180 degrees so that they cancel out. So that's the point that we need to prove. So let me name it as point number A, point number B, point number C, and point number D. Now let's start from point number A. A wave which is moving from A to B, and then from B to C, and then eventually reaches point D. There are two waves, B1 and B2. Now let me use red color again. So here a split occurs at point number A, a split occurs, energy goes downwards. Again at point number B, a split occurs, some part flows in this direction and some flows in downward direction. Now if we look at this portion, I said the distance between these two holes is an odd multiple of lambda by 4. It is 2n plus 1 lambda g upon 4. So the path difference between the two waves B2 and B1, the path difference between these waves can be found as, so this has to travel, let us say this n, as I said, 2n plus 1, n can be 0, 1, 2, so on. For simplicity, let's assume n is 0. So n is 0 would mean the distance between these two holes is lambda g upon 4. So this distance, this separation between the holes is lambda g upon 4. Now, a wave which gets split at point number A has to travel a distance extra lambda g by 4 plus lambda g by 4. Lambda g by 4 from this point to this point, and lambda g by 4 from A to B, lambda g by 4, and from point C to D, another lambda g by 4. So the wave B1 has to travel an extra distance, B1 minus B2. So the path difference can be obtained as B1 has to travel an extra distance of lambda g by 4 from A to B and lambda g by 4 from C to D. So it is 2 lambda g by 4 would be the path difference. So it is lambda g upon 2. Now what is the phase difference corresponding to a distance of lambda g by 2? Phase difference would be 2 pi upon lambda g into path difference. So it is 2 pi upon lambda g into path difference is lambda g upon 2. So it is lambda g cancels, 2 cancels pi radians or 180 degrees. We know if the path difference between two waves reaching a point, for example, we have two waves, if the path difference between them or the phase difference between them is 180 degrees, they cancel out. So the waves B1 and B2 on reaching port 3, they cancel out. So the backward waves cancel out. Therefore P3 is 0. Now if we look at the forward waves F1 and F2, as I said, this forward wave is F1 and the forward wave is F2. This is F1 and this is F2. They have to travel the similar distances. The distances, as for example, I can show you from the figure that the length of the path from point A to B to C is the same as the length of the path from A to D to C. So this length of the path from A to B to C is the same as A to D to C. So in this case the two reaches, the path difference is 0. The path difference is 0. So that would mean a phase difference. The phase difference is also 0. When the phase difference between these two forward waves F1 and F2 is 0, they simply add up. So we receive some power at port number 4. Power received at port 4 is non-zero. So now let's try to find the S matrix of a directional coupler. S matrix of directional coupler. Now since it is a 4-port junction, a directional coupler, as already discussed, it is a 4-port junction, so its S matrix would be a 4 cross 4 matrix. So S matrix should be something like S11, S12, S13, S14. So this is its S matrix. But we know that all the four ports are matched. So that means the diagonal elements must be all zeros. S11 must be 0, so must be S22, S33, S44. All these S parameters, S11, S22, S33, S44 must be 0, as the ports are all matched. And again, as I said, that the ports 1 and 3 are isolated and ports 2 and 4 are isolated. Ports 1 and 3 are isolated means S13 is 0, and ports 2 and 4 isolated would mean S24 is 0. So I can write here, since ports 1 and 3 are isolated, so are ports 2 and 4. So that means S13 is 0, or for that matter S31 is 0. Likewise S24 is same as S42 is 0, as these ports are isolated. Also, since it is a symmetric junction, as can be seen, we have this as a symmetric junction. This is a symmetric network. Ports 1, 2, 3, 4, as can be seen, it is a symmetric network. If we feed a signal at port 1, by that I mean if I feed a signal at port 1, I receive power at port 2 and power 4, nothing at port 3. Likewise, if I feed a signal at port number 2, I receive power at port 1 and port 3. I don't receive anything at port 4. So that way it is a symmetric network. Now moving to this point number 3, as I said, it's a symmetric network, so that means Sij is same as Sji, which in turn means S23 should be same as S32. Ijth element is same as Jith element. S13 is same as S31. S24 is same as S42. S34 has to be same as S43. Likewise, S41 is same as S14. So therefore I can write the S matrix as 0 S12 0 S14 S12 0 S23 0 0 S23 0 S34. This will be S41 is same as S14. This is 0 S2442 is 0. S34 is same as S43, so I'll write S34. This is S44 is 0 as the ports are perfectly matched to the junction. So this is our S matrix. So I have 4 unknowns here. I need at least 4 independent equations. So now from, we know this is a lossless network, and for a lossless network, S into S conjugate is a unit matrix. So let me write S as, this is our S, and its S conjugate would be that we have to replace these elements by their complex conjugates. So our S is 0 S12 0 S14 S1 oh. S14 S12 0 S23 0 0 S23 0 S34 S14 0 S34 and then a 0. Its conjugate simply would be 0 S12 conjugate, 0 S14 conjugate, S12 conjugate, 0 S23 conjugate, 0 0 S23 conjugate, 0 S34 conjugate, S14 conjugate, 0 S34 conjugate, 0. This has to be equal to a unit matrix of the same order: 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This is the unit matrix. So if I multiply row 1 with column 1, I'll get the first diagonal element. On multiplying row 1 column 1, so 0 into 0 is 0. S12 square mod S12 square plus mod S14 square. S14 into S14 is mod S14 square is equal to 1. Let's name it as equation 1. Likewise, if I multiply row 2 with column 2, row 2 with column 2, I get this diagonal element: S12 square plus S23 square is equal to 1, equation number 2. And on multiplying row 3 with column 3, row 3 with column 3, I'll get this third diagonal element. This is our row 2 column 2, this is row 3 column 3, would be S23 would be S23 square plus S34 would be S34 square is equal to 1. This is equation number 3. If I multiply any other row, for example R1 with any other column with column 3, I'll get a 0 in that case, row 1, because non-diagonal elements in this unit matrix are 0. If I multiply row 1 with column 3, for example, I'll get row 1 with column 3. Row 1 is S12 S23 S12 S23 conjugate plus S14 S34 conjugate is equal to 0. This is our equation number 4. So we need 4 equations, as I said, because we have 4 unknowns. So if I look at equation 1 and 2, on the right hand sides we have 1, so the left hand sides of equation 1 and 2 must be equal as well. This left hand side must be equal to this left hand side. So on comparing them, what I get is that S12 cancels, S14 has to be equal to S23. So S14 would be equal to S23 from equations 1 and 2. Likewise, if I look at equations 2 and 3, on comparing equations 2 and 3, we have 1 here, 1 here, so their left hand sides must also be equal. On equating their left hand sides, s23 and s23 cancels out, s23 cancels out. We are left with s14 square. Equations 2 and 3, I'm saying that s12 square must be equal to s34 square. So that implies s12 is same as s34. So s14 is same as s23 and s12 is same as s34. Now if I assume that s12 is real and positive, that means s12 is same as s34, as we have proved. S12 is same as s34 is equal to p, and it must be equal to s34 conjugate as well, because if I have a complex number which is purely real, so it is conjugate. If c is a plus iota b, if it is purely real, if it is real means b is 0, so complex number is real. So it is real. The conjugate of a complex number which is real is the same number. The conjugate would be again the same real part. So that means s34 would be same as s34 conjugate. So in this case, s12 is s34 is p, which is a real quantity, has to be same as s34 conjugate. Now if we look from equation, say for example, we have from equation 4, let me rewrite equation 4, s12 s23 conjugate plus s14 s34 conjugate is 0. Now we are saying that s12 is same as s34 conjugate is p. So this is p and this is p. p into s23 conjugate plus s14 conjugate is equal to 0. But s14 is same as s23. We proved it somewhere. s14 is same as s23. So I'm writing it as, that means s14 conjugate should be same as s23 conjugate. So which in other words means, from this equation, p into s23 conjugate plus s23 conjugate this is s14, here it is not s1, it is s14. So p into s23 conjugate plus s14 conjugate is 0, but here I can write as p into s2, from this equation I can write p into s23 conjugate plus s14 is s23, s14 is same as s23, so I can write it is s23 is equal to 0. But p, as I said, is a real value, cannot be equal to 0. That means s23 conjugate plus s23 is equal to 0. But we know if the sum of a complex number and its conjugate is 0, that means the real part is 0. Real part of complex number is 0. So real part of a complex number is 0 means the complex number is purely imaginary. Let us assume s23 is some imaginary number jy. So this part, let me explain it. If we have a complex number and it is conjugate 0, this means real part of complex number is 0. So that means z, the complex number, is purely imaginary. So that's what I am saying. S23 is some complex number which is purely imaginary, so S23 is jy, or S23 is j some q. Let's write q instead of y. So S23 is a complex number jq. So what we have obtained is that S23 is same as S14 is JQ, and S12 is same as S34 is P. But from equation 2 above, from equation 2, we know, say from equation 2, we have S12 square plus S23 square is 1. S12 square plus S23 square is 1. That means P square plus S23 is JQ. The magnitude of this complex number would be simply Q. That would mean magnitude of S23 is simply Q. So P square plus Q square is 1. Now let me write the S matrix then. So the final S matrix of this directional coupler is 0, P, 0, JQ. P, 0, JQ, 0. 0, JQ, 0, P. JQ, 0, P, 0 is the final S matrix of our directional coupler, two-hole directional coupler. So again, we can see from this, if we look at a lossless junction, we know for a lossless junction the sum of squares of any column must be 0. The sum of squares of S parameters of any column must be 0. That means P square plus Q square is equal to 1, which is same as that. Now say in general, if I have a lossless network S11, S12, S13, S21, S22, S23, S31, S32, S33, if this is the S matrix of a lossless network in general, then the sum of squares S11 square plus S21 square plus S31 square must be equal to 1 for the network to be lossless. If it is less than 1, then it is a lossy network. So this is all we have for the day. Good day.